Today we want to look at solving trigonometric equations. We just want to introduce the idea of solving trigonometric equations and think about the new complications that are going to arise because of the word that we've added to the solving equations. That's the trigonometric part. To that end, we want to tie this to the stuff that we've been doing recently, which is graphs of sine waves. And we want to visualize solutions of equations as intersections of graphs. So that's where we're going to start. We're going to imagine solving equations by thinking about intersections of graphs. So let's suppose that we have some function. I'm going to have the generic name function f of x. I'm also going to write suppose the way we say suppose. Suppose. We need to use the apostrophe more. It helps a lot if you can't remember how to spell a word. Just leave off the letters that you're unsure of and put an apostrophe, because that's what the apostrophe is for. So let's suppose we have some function f of x. We want to think about solutions to equations as intersections of graphs. Let's suppose that this is the graph of f of x. We want to think about different solutions. We want to think about what gives us solutions to equations and how they're related to the way we visualize our functions. So here's a visualization of a function. If we think about this graph and its relationship to the x-axis, let's suppose that we have an x-axis. The x-axis is the line where y is equal to 0. So the equation for the x-axis is y equals 0. So if we wanted to solve the equation f of x equals 0, we're looking for where the graph of f of x crosses the x-axis. So the solutions to the equation f of x equals 0 will be the places where the graph of f of x intersects the x-axis, known as the x-intercepts of the graph. So we can see if we were solving the equation f of x equals 0, in this scenario, we can see 3 solutions. We can see 3 solutions in this case. Now, this is if we have the function f of x equals 0, or the equation f of x equals 0. We don't always want to have f of x equals 0. So let's suppose that we wanted some other, we have some other equation where f of x equals some other constant. I have no constants here, so I just have to draw another line. So let's suppose that we have some other line up here. Let's suppose we have this horizontal line. The equation for a horizontal line will just be y equals some constant. I use k, the mortal constant. If we wanted to solve the equation f of x equals k, we'll look for intersections between the function f of, or the graph of f of x and the horizontal line x y equals k. So in this case, we can see that there will be two solutions. Looks like this graph hits this peak right here, and then it crosses again over here. So it looks like we have two solutions in this case. It might be that we have not just f of x equals some constant, but f of x equals some other function entirely. So we have this graph of g of x, some other function entirely. If we're looking for solutions to the equation f of x equals g of x, we can just see where the graphs of f of x and g of x cross. So it looks like in this case, we'll see 2. Depending on what's going on where we can't see what's going on. We're looking for points of intersection between the 2 graphs, the graph of f of x and the graph of g of x. Two, unless there's something going on with these tails that we just can't see. There's 2 that we can see, and I try to draw those these two branches down here is looking like they're parallel. But there might be some other intersection depending on how those things are bent. If the blue graph is falling faster than the black graph, then they won't intersect again. But if the black graph is falling faster than the blue graph, then there'll be some other intersection that we just can't see because we're looking too closely. If I put that on a test, that would be a real jerk move on my part. You're like, oh, you didn't see this one down here. I can't show you the things that you have to work with, right? Oh, secretly, this graph turns up and then goes back and forth a bunch of times. This happens off screen. Point is, when we're solving equations, we're looking for intersections. Even though it doesn't look like we're looking for intersections, we're trying to do the same thing to both sides of an equation. We're still looking for intersections by doing that. So mechanically, we don't really think of this that much. We think of doing the same thing to both sides of the equations. This is useful in case we don't know what to do to both sides of the equations, especially with the amount of computing power that we're all carrying around. If we can just produce graphs of things, then we can solve equations just by looking at the graphs of those things with maybe a graphing calculator. Not like the Texas Instruments graphing calculator, that's a terrible graphing calculator, but if we have a better graphing calculator, then we can just look at the pictures, look at the graphs, find out where they intersect. Any questions? Comments? Snide remarks? No, you're just trying to get through the next 2 hours so you can get to spring break, at least math spring break. I don't know if you have classes tomorrow. So like, well, I just need to get to math spring break. Then I could not have to listen to Leach for another 12 days. I'm going to put all my videos, just make sure they're all muted. I'll kill the sound so you can't even hear my voice if you watch the video. I'm just kidding. No one's going to be watching my channel during spring break. It's funny because YouTube does like analytics, even like with tiny channels. It's like, oh, look at your daily views. I'm like, oh, 5 people watch my videos. So like during the semester, it's like, oh, and then you could tell when we're between semesters because like, oh, no, fuck that guy. And then actually every once in a while, like during the summer or during winter break or during spring break, I will get a view on YouTube because a couple of years ago I sold a guitar amp and I recorded video that just verifying that the amp still worked. And I left that video up because it's my most popular video. So people are like, oh, a twin reverb. Yeah, check this out. It's me I'm not playing anything except I'm just like, I'll show you that the knobs work and that the foot switch works and shit. Anyway, what are we talking about? Oh, yes. The important thing was I was working on my actual current project was to stop doing like long form videos that are recorded before a live studio audience and try to summarize trigonometry in like TikTok videos, like 1 minute at a time. Can you do trigonometry 1 minute at a time? Just like 1 minute. It's like, oh, boom, there's just watch 1 minute of video and then do some stuff. You watch 1 more minute video. I don't know. Can you just TikTok all of math? That's beside the point. So we're thinking about these intersections with graphs of functions. And we want to think about what happens when we start using trigonometric functions. In particular, sine waves. So like suppose that we're looking at the graph of just plain old sine x. I know normally we use theta, but we use sine or x. So let's suppose we have the graph of sine x. And we want to find out when sine x is equal to 1/2. So I want to solve sine of x is equal to 1/2. This would mean that we're looking for points of intersection between the graph of sine x and the horizontal line y is equal to 1/2. The horizontal line y equals 1/2 will cut through here at 30 or pi over 6 in quadrant 1 and quadrant 2. And you should be all suspicious. Why is the red line going all the way across the page? So we see these two solutions, pi over 6 and 5 pi over 6. And we can see that's the first quadrant and the second quadrant where sine is positive. So we can see that we're going to have pi over 6 and 5 pi over 6. Thinking back to the stuff that we've done before, that'd be 30 degrees in quadrant 1 and quadrant 2. Or pi over 6 radians in quadrant 1 and quadrant 2. This is the graph of sine between 0 and 2 pi. So if we wanted to solve this equation for x between 0 and 2 pi, there it is. Pi over 6 in quadrant 1 and quadrant 2. So pi over 6 and 5 pi over 6. How many solutions do we have? How many solutions do we have if we don't have restrictions on x? Infinitely many, because what does this graph do? It just does this over and over again. This graph is going to keep going across pi over going across 1/2 because this graph just goes on forever and ever. From 2 pi to 4 pi, we're just going to see a copy of this same cycle. That went farther than 4 pi. So we also see 2 more solutions in the next go around. And then after that, we'll have even more. So in the next cycle, we're going around the circle again, and we see 2 more solutions. If we think about what happened before 0, we have 2 more before then. From negative 2 pi up to 0. So there's a lot that we have to consider if we're going to start solving trigonometric equations. Any questions? How's everybody okay? It's like all 1 hour and 15 minutes to go. And then some of you are like, oh no, you're not going to do a whole hour and 15 minutes, are you? Well, yes. No breaks. I'm just going to talk the whole rest of the time. Maybe I'm just going to use this voice too. I need more, get more coffee. I just switched to soothing voice. And so we see we have infinitely many solutions. There will be many solutions. You have to find a way to get them all. Everybody's asleep, and I'm just like, oh. But when you come back strong. And so, and then everybody goes, right? So. Favorite incident of student falling asleep in class was actually during a final exam for a summer class that I was giving. And the student did like 0 work. Showed up to the final, and I go, all right then, here you go. Dude fell asleep during the test. Now, I didn't really notice because I kept having to answer questions and stuff like that. But so I didn't really notice. I didn't really worry about it that much because they were almost never there, right? So I'm like, oh, I can't worry about everybody. I can't fix everything. The problem was less that he fell asleep during the class, but more that he's a drooler. And he tried to turn in the test anyway. And I'm like, oh no. So because he was like, right? And I go, all right, turn in your test. It's like, and it was like, and I'm like, oh, he's just gonna trash it, right? Certainly he knows. Not, and then he's like walks up, he's like holding it flat, like to contain all the drool. I'm like, are you serious? And cause he's like walking up and go, okay, at this point he can still go and put it in the trash can. He can still go and put it in the trash can. I go, dude, the trash can's right there. Trash can's right there. What are you doing, man? And then he like puts it down on my desk and I'm like, no, before it hits the desk. I'm like, oh, no, go ahead and put that in the trash. I'll give you another one. You can put your name on that one. And it will take you as long as it takes to write your name to write everything that you need to write because you didn't write anything. Unless I'm supposed to like somehow read the drool as your answer. So anyway. What are we talking about? Oh yeah. We have infinitely many solutions. So we see that we have infinitely many solutions. We want to see what, and we want to take this and figure out what we have to do because solving equations is way more than just doing the same thing to both sides of the equation. So let's look at the different levels of solving trigonometric equations. Let's look at the different levels of solving trig equations. And we're going to start with only the most basic of things. And I'm going to keep using sine of x equals 1/2. Actually, we'll start with, let's just call this inverse function. Sorry. I've called it calculator in the past, and every time I call it calculator, I keep wanting to say, let's call it inverse function. So first level, just doing it inverse. This is the level of do the same thing to both sides of the equation. So the inverse trig function. This is our first level because it's only going to give us one value. If we ask the calculator what angle has a sine of 1/2, we're just going to get one answer. It's going to tell us pi/6 and that's it. So in this case, we're only going to get one answer. So I say if sine of x is pi/, looking into the future. If sine of x is equal to 1/2, we know we can grab our calculator and say, hey, calculator, what is the sine inverse of 1/2? Okay, we can't literally say it unless we have voice activated calculators. But we can say, hey, calculator, what is the sine inverse of 1/2? And it'll tell us pi/6. Everybody recognize pi/6, right? Not a quiz on it, so just be like, oh yeah, totally. See, there's pi divided by 6. So we ask the calculator and we say, what is the sine inverse of 1/2? And the calculator says pi/6. It just says it in calculator speak. That's how the calculator says pi/6. We're only getting that one answer. When we use the inverse sine, it gives us an answer from quadrant 1 or quadrant 4, and it gives us a negative value in quadrant 4. But when we use the inverse trig function on our calculator, the problem is we're only getting one answer. We know that there's more than one because we're sophisticated trig students. We can take the reference angle. We can take this inverse trig function to be a reference angle And we know about quadrants. So sine of x is equal to 1/2. We know there's a pi over 6 in quadrant 1 and a pi over 6 in quadrant 2. So here we're going to get two answers. So in this case, we'll usually get two answers. It says we'll start with sine x is 1/2. And we know the reference angle part is we'll get pi over 6. But now we'll include the quadrant parts. This is pi over 6 in quadrant 1 and quadrant 2. So we're going to get two answers. So the quadrant 1 answer is pi over 6. And the quadrant 2 answer is 5 pi over 6. But we know more stuff now. That's the problem. We know too much now. And it makes us unhappy. Ignorance is bliss. Knowledge is annoying. The more you know, the worse you feel about stuff. If you want to be happy, stop going to school because you get more information. And you're like, oh man, that's kind of depressing. But wait, there's more because we know these functions have cycles. Sine has a period of 2 pi. So these are the first two. This is just going once around the circle, but we can go forever around the circle. But there are infinite cycles. It's okay. The cycles have a period. Each cycle has a given length. So if we want to know when sine of x is equal to 1/2 forever, we know the reference angle is pi over 6. It's in quadrant 1 and quadrant 2. So that gives pi over 6 and 5 pi over 6. Here's where we're going to list the infinite solutions. Here's where we're going to list all the solutions. We got pi over 6 in quadrant 1 and quadrant 2, and we know that this happens every single cycle. So we're going to add multiples of the period. We're going to add multiples of the period. What that looks like is we say pi over 6 plus 2 pi plus 4 pi plus 6 pi minus 2 pi minus 4 pi minus 6 pi. We're going to add multiples of 2 pi because that's the period for the sine function. Here I've just added 2 pi one time. So if I want to do this for a bunch of times, I say plus 2 pi n for n in z. Z is our abbreviation for integers. So this is how we'll say for all integers n. This is us adding 1 pi and 2 pi, or sorry, 1 full period, 2 periods, 3 periods, 4 periods, 5 periods, and so on. Also subtracting 1 period, subtracting 2 periods, subtracting 3 periods, subtracting 4 periods, and so on. And we do that to both of these. So here's how we can list all of the solutions, because it's very predictable how far apart the solutions are. Any questions? So that's n, and then it's is an element of. So this symbol here, make a like a C, and then like put a line through it. This is the symbol for is an element of. And then the Z, it looks like a 7, then an upside down 7, or an italicized L. It's a double Z. I should really connect these. And that's our abbreviation for the set of integers. Obviously, we want to use Z for integers because of all the times that the letter Z shows up in the word integers. I think it's actually because like we didn't want to use an I, and so we just kind of like shoved it over and it kind of became a Z. Z is just an I with some frame damage. Any questions? So it's based on the things that we've done before. We have to, at this point in our mathematical careers, we have to start thinking of solving equations, not just by doing the thing to both sides of the equation and maintaining balance. That's where we start solving equations, just like mechanically doing the same thing to both sides. The problem is the sine function is not invertible. If we just grab the inverse sine function, that gives us one solution. And we know that there are many more than that. So we just need a way to find out those many more solutions. How's everybody okay? Let's take a quick break. Come back at 10 o'clock, 10 minutes after 1 o'clock on April 2nd. That's going to do it for this week. That's going to do it for next week as well. I will see you all after spring break on April 2nd. Everybody have a nice spring break. And thanks for playing.